So, good morning, good afternoon, good evening again, everyone, depending on wherever you are joining from. I extend a warm welcome to all of you to the second day of the user preparation webinar on next generation spectral images. That's FCI, the flexible combined imager on board the next generation geostationary satellite METIOSAT third generation MTG, and the METimage on board the METOP second generation, which is our next generation polar orbiting satellite. I'm Srireka Thoniparambil. I'm managing the EPS-SG user preparation project at EUMETSAT, and I'm organizing this together with my colleague Stefan Brzezinski. He is the MTG user preparation manager. And this is the fourth webinar in our series on next generation user preparation webinars on all observation missions that are on board MTG and EPS-SG programs. So the MTGI satellite, which carries the FCI, the flexible combined imager, will be launched next year, end of 2022, and the METimage, which is on the METOP-SGA satellite, will be launched. The METOP-SGA satellite, which carries the METimage instrument, will be launched in early 2024. So this is why we are targeting these webinars to all potential users of FCI and METimage. For those who were with us yesterday, I'm happy to see you all back, of course, but I also hope that you had a useful close to 3 hours of knowing more about the FCI instrument, the level 1 data, the performance, product formats and dissemination, and also the SIFT PyTrol readers, the application perspectives, etc. Today, we take a similar journey through METimage. We would focus today on METimage. It's a vital mission and a follow-on mission of the AVHRA satellite. It's AVHRA, which is on board the current METOP satellite, but with an enhanced capability in terms of spectral information, spatial resolution, etc., etc. It has similar capabilities to the NOVA VIIRS, and I think it would be really exciting to complement what VIIRS now offers on an afternoon orbit. So in that way, today we look more at the level 1 data from METimage. So how it's measured, level 1 products, format and dissemination. Again, we will have a demo of the SIFT and the SIFT demo. We will have also the RGB presentation as well. And tomorrow we will look more at the geophysical level 2 products that are generated at the EUMETSAT central facility. So just before we start, a few points before we ask Pepe to present the talk on METimage. I have to remind you that we will use the tool called Slido to ask questions to the speakers. And information will come up in the chat window on how to use it. Just type slido.com and then ng-images. And then you are there and you can ask your questions. You can also open the tool in your mobile phones or also on your computer. And we will try to answer most of the questions today. We have, I think, enough time to answer questions. And if not, we will take them offline and provide you the answers. You can use the Slido in various forms. You can also vote for the questions that you like. You can also reply to the questions, make comments, actually, if you would like, and restrict the Zoom chats to technical issues. If you can. And let me remind you that we will provide all the presentations, the Q&A with the answers, and also the recording after the event. So with that, I hand over the session to Pepe Phillips. She will talk more about the METimage instrument. Pepe, over to you. You can switch your video on. Yeah.
Okay. Hello, everybody. So good afternoon to all those in Europe. Good morning to all those in the West, and good evening to all those in the East. I shall get my presentation started. Hang on. I need to, where is it? Share screen. Brilliant. Can you all see my screen? And hopefully now the title page should come up.
Looking good, Pepe.
Looking good? Okay, then we'll start. So the first presentation I will give today introduces the instrument, so the METimage instrument, the scanning mode, spectral properties, performance requirements, etc. Just have to keep moving the window around. So first of all, I will begin by introducing METimage and the EPS-SG mission in general. So that's then I will then go on to the observational requirements, which define the instrument itself. METimage is driven by user needs, and the observational requirements are what we initially analysed in order to sort of develop the instrument, and that's what's made it what it is. I will then describe the instrument and the scanning geometry, then go through the performance requirements, and finally the calibration concept and just a little introduction to the level 1 processing. So to introduce the instrument, we have the visible infrared imager mission, which is fulfilled by the METimage instrument. So just to clarify that, at the very beginning, when we were in the EPS-SG definition process, we had a need for a follow-on from AVHRR. So we needed a visible infrared imager of some sort. So that the VII, which is obviously the abbreviation of this, is the name given to the mission, which was then fulfilled by the METimage instrument, which is currently being procured by DLR, the German aerospace agency. And the VII or METimage is, so the two are effectively synonymous now. So mostly we use the name of the instrument METimage, but you may now and then see VII, so specifically like for the channel numbering scheme and name. So the two are the same now. So the METimage is a scanning optical imaging radiometer serving operational meteorology, climate and oceanography and land monitoring. It records a gapless image with a swath of 2,700 kilometers with 24-hour global coverage. And we have 20 channels ranging from the visible, so from the lowest channel is 443 nanometers, through the near infrared, shortwave infrared up to the IR, where our last channel for sort of cloud top height, CO2 channel, is at 13 microns. We have a ground resolution of about 500 meters at nadir. At the swath edges, the pixels grow to about roughly about a factor of 5 in the across track direction, factor of 2.5 in the along track direction. We have, it is effectively, from the European point of view, the follow-on to AVHRR. But the instrument is very different. It's much more comparable to modospheres. Of course, AVHRR has been flying a very long time and technology has moved on. So METimage is a substantial jump from AVHRR, and you'll see this in the following slides. Wrong way. Okay, so just to introduce EPS-SG. So this is the EUMETSAT polar system 2nd generation. And here we are providing continuous long-term data sets in support of operational meteorology, environmental forecasting, global climate monitoring. On the left-hand side here is a picture of the first satellite. So this is satellite A. There will be 6 METOPS-SG satellites of 2 different types. So we have satellite A, which is the sort of sounding imagery platform. And this is due to be launched sort of early 2024. It'll be in a sun-synchronous orbit, sort of roughly 820 kilometers altitude, with the 9:30 local solar time for the equator crossing, sort of 122 orbital period. It's part of the NOAA EUMETSAT joint polar system, where METimage here fulfills the mid-morning orbit and contains instruments procured by generally ESA, but also some that are particularly done by CNES, which is YASI-NG, the follow-on to YASI. Obviously, METimage is procured by DLR, and we have the Sentinel-5 from ESA. Just to give you a quick guide around the platform, we have at the very front the radio occultation antenna. In position 1 is YASI-NG, the atmospheric sounding mission. Position number, I've lost my cursor. It's disappeared. Anyway, there it is, it's back. METimage is here just between YASI-NG and the Sentinel-5, which is the atmospheric chemistry mission, so sounding from the UV to the shortwave IR. And then position 2, we have the microwave sounder, position 5, we have the new instrument, which is the 3MI, which is the multi-viewing, multi-channel, multi-polarization spectrometer, where here we hope to have quite a bit of, be quite nice to have some synergy with METimage. And number 4 is the radio occultations. There's 2. I just confused myself there. I thought I'd already said it, but there's 2, obviously, one at the front, one at the back. So the primary observations. So these primary observations are what drive METimage to be what it is. And they are cloud observations, particularly including microphysical analysis. And this really has driven the performance requirements and the channels that we have. Water vapor imagery, aerosol observations, polar atmospheric motion vectors, Earth surface albedo, vegetation, cryosphere, so anything snow, land and sea ice imagery, fire detection and surface temperature, so both land surface temperature and sea surface temperature. Not all products will be made from these areas and disseminated by EUMETSAT. The SATs will be involved, and I will indicate now in the following slides a little bit more about that. So first of all, just the METimage spectral channels. So the channels in bold are the AVHR heritage channels. So there's these 1, 2, 3, 4, 5, 6, of which 2, I think there was a bit of a switch with the day and night. But you see, METimage has 20 channels now. So it's a big step up from AVHR. So we have the standard blue, green, red channels. Then we have some relatively new, what I call new channels, where we have the channels in the oxygen A band. So there's one just outside the oxygen A band and the second one in slap bang in the middle of the oxygen A band absorption. And this is a very sort of powerful way of getting cloud and aerosol height assessment. We then have the standard sort of 865 imagery channel, a water vapor channel at 900 nanometers. Then we move on to the sort of not quite window channel at 1.2, which is good for clouds, aerosols, vegetation. Then we have the 1.3 micron channel, which is super for high level clouds, cirrus cloud detection. The 1.6, which is very important for cloud phase and also a good window channel. The 2.25, which for cloud microphysical analysis. And then we have a set of channels from sort of 3 to 4 microns. The driver here is the 3.7 is a wider channel, and it's more the generic clouds atmosphere sensing channel. The 3.9 and the 4 much narrower, and these are particularly good for sea surface temperature and fire detection. So they have slightly different sensitivities to water vapor, I understand, and when used together, you can get very good sea surface temperature retrievals with these at night. We then have the 6 and 7 micron channels for the water vapor imagery and the polar winds. The 8 micron channel for cirrus cloud detection, then the classic split window channels, 10 and 12, 10, 11 microns and 12 microns, and then a single channel at 13 microns for cloud top height. So some of these channels we have, they're similar to what's on VIRS, with perhaps there's no day-night band, and there's sort of fewer atmospheric clearing channels and channels related to ocean color. There's obviously similarity to MODIS, but it's sort of a bit like a slimmed MODIS, say, for example, we have one cloud top height channel at 13 microns rather than the full set of 3. And with a combination of the 12 and the 13, you can still get a relatively good cloud top height estimate. It's kind of we had to trade off there. And as I said, we have the additional, we focus more on the sort of atmospheric side, so sensing. So we have the oxygen A band absorption channels, the water vapor imagery, and the other imagery channels at 6 and 7 microns as well. So that's our focus for METimage and EPS-SG, as well as the continuity from AVHR and the new observational requirements. So I will just give a quick run through the observational requirements and the channels and what we get, because a lot of this will be covered separately in more detail in presentations tomorrow, when my colleagues will talk specifically about the level 2 retrievals and what we will disseminate from EUMETSAT. But just to give you the overview of the full observational requirements as a whole, I will just quickly go through. So cloud is our primary observation with cloud optical thickness. In particular, these are largely using heritage visible channels with the addition of the 1.24. Cloud drop and particle effective radius. Specifically here we have the 2.25 micron channel that's particularly high in information content here. Classic cloud imagery using all the standard color composites. Cirrus cloud detection with the 1.38 micron channel and the 8.5 during the night time. Snow cloud discrimination with 1.6, 3.7 microns. Cloud phase at the cloud top, specifically here with the 1.6 micron channel. Cloud top temperature, again, we have a sort of plethora of channels for this, with the oxygen A band channels for daytime, and then the CO2 slicing at the night time, and then perhaps some combination with YASI data from infrared sounding too. Water vapor imagery, we like to look at particularly the displacement of water vapor from subsequent orbits, and this gives us atmospheric motion vectors in polar regions, particularly where you have the high refresh rate and overlap, and Regis will talk more about this tomorrow. In the near infrared, we have one water vapor channel at 914. Those of you who are familiar with MODIS, you'll notice that there were several channels in this region, sort of some in the high absorption, some in the low absorption area of the water, so you don't water vapor depend, then you can sort of trade off with the saturation. We have a sort of wider channel that's not too strong in the absorption, but not too far outside. So hopefully there we can get a good all-round sort of global water vapor measurement. And in the thermal infrared, we have the channels from 6 to 8 microns to support the measurement of water vapor total column. And I think Loredana is going to talk about that tomorrow. Aerosol can be measured at several wavelengths in the vis and near infrared. At EUMETSAT, we have no centrally generated aerosol product, but the atmospheric chemistry SAF will be active here. And with these channels, with the wavelength dependence, we can get the aerosol optical depth, and the angstrom coefficient will give us indication of the aerosol size distribution. And the choice of the retrieval will depend largely on the scene and which channels are used to get the good contrast. Even I think the oxygen A channels can be used for the aerosol, in particular the aerosol height. And of course, for all these observations, the cloud distribution is fundamentally important. So of course, we need other channels in order to get the cloud properties in as a precursor to the aerosol retrievals. Then we have land and sea surface temperature. Of course, we have the split window channels, which are fundamental to land surface temperature and sea surface temperature. And as I mentioned earlier, we have a set of channels at 3.7, 3.9, and 4 microns for sea surface temperature. And yeah, because these channels are very sort of sensitive to surface temperature and surface leaving radiation, but they're contaminated by reflected solar radiation, so they're sort of restricted to nighttime use only. But then we have the 10 and 12 microns for daytime use. And the 4 micron channel is an additional channel which helps with sea surface temperature because it helps with the detection of the atmospheric variability. Then for the cryosphere, we rely on the high reflectance in the short wave and the low reflectance values in the mid-infrared. So sort of using the combinations of channels, we can then see the different contrasts. And we hope to get snow cover, snow albedo, sea ice cover, land ice cover, depending on the land-sea distribution. Again, we don't centrally distribute snow and ice products, but the land SAF and the ocean SAF will be, again, active here. The visible and near-infrared channels will support these observations. Again, to get the contrast between some of them that show snow dark and others that show snow as light. And then we have snow and sea ice temperature observations, which require the split window channels. And vegetation, again, with the visible channels will be used heavily here. We will look at the photosynthetically active regions of the spectrum, and using combinations of visible and near infrared channels, we can generate normalized differential vegetation indices. Oh, there's a mistake there. It says a high resolution channel. There are no 250-meter channels. That's out of date. All the channels are 500-meter spatial resolution. So, and as with other surface observations, sort of a good characterization of the atmosphere is prerequisite. So all the clouds and other atmospheric channels are needed here. And last, we have the fire. We have the 3.95 channel for detecting fire. We have no high dynamic range channels, so fire radiative power will not be possible with METimage, but with the 3.9 we can, and the combination with the 1.6, we will be at least be able to detect fire, do something maybe with smouldering fires that aren't too high temperature. And again, the split window channels will also support here with the cloud screening, and the visible channels will obviously provide smoke plumes. And in the Landsat, again, we'll be looking at these products. So now to change this up, so these are the observational requirements that drive the channels and the instrument and why it is as it is. To talk a little bit now about the instrument itself and the architecture. So the METimage instrument consists of a rotating scan mirror followed by a telescope, a derotator assembly in order to compensate for the rotation of the image. We then have in-field separation of spectral channels, and effectively we have 3 detector planes with rows of detector elements for the different spectral channels side by side in an image plane. And essentially, as the instrument scans, the image moves sequentially over each of the detector rows, i.e. different detector channels, and we get basically the wavelength selection from a filter, so a coloured filter effectively, that is mounted then in front of the detectors. So we have these 3 detectors, and the channels are divided amongst the detectors. So from 400 to sort of 900 nanometers is on the visible focal plane. From 1.2 to 4 microns is on the mid-wave, short-wave IR focal plane. And then from 6 microns down to 13 microns, these are on the long-wave focal plane. And just as a quick schematic of the instrument here, so we have the scan mirror. This is the part of the instrument that then sees the Earth, scans, and then transfers the radiation from the Earth and then into the instrument. The telescope reflects it about a bit. Then we have this clever device called the derotator, which is really fundamental for actually focusing the image on the focal plane, because the scan mirror is moving, and if the scan mirror is moving, the image is moving and rotating with the scan mirror, and this derotator compensates for that rotation, which then means that there's a fixed image on the focal plane, and the only movement there that's occurring is that the image is moving subsequently across the detector elements on the focal plane, so that then we then get a reading for each different channels. That does mean that for each observation there's a minute difference in time for each of the acquisitions for the different channels, but they are co-registered to the same point on the ground, and the timing difference is absolutely minute. It's something like, the difference between each one is something like 200 microseconds, so there's no change in the scene between the measurements. We then have a beam splitter assembly, and this beam splitters, there's 2 of them, and one strips off light and sends it to the visible focal plane and lets the rest through, and then the next one splits between the long wave IR and the short wave IR. We then have cryo mask, cryo window. We have the 2 of the focal planes are cooled. They then have some relay optics behind them, which then compresses the image a little bit, makes it a little bit smaller so it fits on the focal plane better. And then the detectors are cooled. In particular, it's very important for the long wave IR. It has to be cooled quite a lot, otherwise you have too much noise in the 13 micron and to some extent 12 micron channels as well from the dark current. So the cooling there is very important. So just some pictures just to quickly show us a schematic representation of the instrument here with the optical head, which then looks at the Earth. This is the ESCAD baffle. So this big thing here baffles sunlight away. We have a solar diffuser for the solar calibration, and that sits inside this part of the instrument. When I can find my cursor again, it's disappeared. Never mind. Anyway, we have a cryogenic subsystem, which will then house the 2 focal planes, which I mentioned, to cool the longer wave ones, and then external electronic assembly. There is also another calibration device. There is a black body for the thermal calibration. That is actually on the floor of this picture here. So down at the bottom underneath is the black body situated. And just to show you with the optics, here is the scan mirror. So the light comes in. We have an entrance pupil, various mirrors. And this is the derotator. This is the bit that stops the image rotating. And then the 3 focal planes at the different parts here, of which the last two are cooled, and then the various beam splitters. And Airbus have kindly sent some photos of the actual instrument being integrated and assembled at their clean room facility in Friedrichshafen. So this here is METimage, as is this here. I think here they are just, I think it's just integration work going on here in the clean room. Then this is actually, on the left is the cryogenic subsystem. I believe this is it as well. So again, in the clean room facility at Airbus Friedrichshafen, Airbus are building the instrument. And then now to come to the scan geometry. So it is a cross-track scanner with a 2,700 kilometer swath width. So it's sort of plus or minus 53 degrees scan range. We have a 12 kilometer swath width in the along track direction. So effectively, what happens with METimage is it's compared to AVHR, it just acquired scanned relatively fast and just scanned a single line of pixels in one scan. With METimage, because we have higher performance requirements and signal to noise, the instrument has to scan slower in order to have enough time to acquire all the data it needs. But the instrument is still in the same orbit, so its ground speed is still fast. So in order to have complete coverage, it has to measure more than one line at the same time. So this is why we have these 24 long track pixels. So we have more than one scan line of pixels acquired in a single scan. And that has impacts on the scan pattern on the ground, which I will discuss later. It's a continuing scanning instrument, but it accelerates over the back of the instrument. So in order to optimize signal to noise ratio, we have constant scanning speed over the front of the instrument. But then once we get to the back of the instrument, it then accelerates over the back of the instrument until it gets back to the calibration targets. There are various different scanning modes we can use to sort of control where this acceleration exactly occurs. For example, if there was a lunar calibration event, it would start after the deep space view. So the scan profile is configurable, and we also have regular views to calibration sources. So there is we have the Earth view, so at TX0 we scan constant speed around the Earth view. Then we have the deep space view, which is needed as the cold point for the 2-point calibration. We accelerate over the back of the instrument, come back down to normal speed for the solar calibration device, for the solar channel calibration, and then for the thermal calibration for the black body. So, as I mentioned, we measure 24 samples simultaneously in the along track direction. I use ALT for a long track abbreviation and ACT for a cross track. So a long track is this dimension here, and a cross track is the bigger one. So we have 3,000 in a product, 3,144 cross track samples per scan, and in the along track direction, 24 along track samples. Now, this diagram here is very, very exaggerated, but it's just to illustrate the point that at nadir, the swaths match up sort of more or less continuously. Technically speaking, depending on where we are in the orbit and the actual height, they either may slightly overlap or just about come together. So it's not completely continuous. But at the swath edge, because the swath is big, and here we are on the major arc, here we are on the minor arc of the Earth, so the curvature is much, much higher. So the effect is that these swaths splay out and, of course, overlap. So the corners of one swath cover the region of another swath. So we have what we call these bow tie effect, because they look a little bit like bow ties. In reality, on a single ground, you can hardly see it, but it's nevertheless there. So neighbouring swaths do overlap at the swath edges. Now, for METimage, we do downlink all the data, including the overlap areas, and there is a mask containing the level 1 product that would enable you to say, okay, if I don't want to view the overlap regions and I just want my product continuous, which pixels do I have to take from this swath? And there is this mask it's a 24 by 3,144 mask that would then enable you to then select exactly which pixels to use, and then you have a continuous product. So now come to the performance requirements. So as you see, because of the more sophisticated parameterization of clouds and surface properties needed, drives the spectral and spatial resolution of METimage. So first of all, we have 20 channels rather than 5 channels as for 6 channels for AVHRR. And we have a 500-meter spatial resolution instead of 1 kilometer. And this factor of 5 really does drive the instrument, because every time you make a pixel smaller, there's less light going in, and the less light you have going into an instrument makes it more difficult to get a good performance. And just on the right here, we have just a quick comparison. You can see this is just between AVHRR and MODIS of this estuary region here, and you can see straight away from the improvement of the spectral resolution and the spatial resolution, you have much more information in your image. This slide's a bit of a headache, but what I want to just show is that we have the central wavelengths here on the right, and these are the signal to noise ratio requirements for the solar channels and the NE delta T's for the brightness temperature, the noise requirements for the thermal channels. And just I would highlight here that all our requirements are specified at typical scene temperatures, although they have to be met for the full dynamic range as much as possible where feasible. And these typical temperatures are, okay, give the example for the solar channels, we want a typical temperature that is low temperature still, but representative throughout the orbit. There's no point defining the instrument for the extremely low temperature case, which only crops up like once every 5 orbits or something. So we define everything for the challenging scenes, but at least representative scenes, and that's what these typical temperatures are. And you can see here in the columns, if you're interested, what the dynamic range is, and then how we define the typical scene temperatures. And just quickly for the other performance requirements, we have a sort of bias error of 5% for the solar channel, half a K for the thermal, lifetime stability of 1%, so over the stability over the lifetime of the mission, 1% for the solar, 0.15 K for the thermal. For interspatial homogeneity, so that's like how, if you look at a constant scene, you don't want your values to change. You know, everything should measure constant, but of course over the full swath that's kind of hard, but we try and do that to within 1% for the solar bands and to within 0.1 K for the thermal. Same with the interchannel homogeneity, instead of being like a spatial requirement, it's in between bands. So bands looking at a scene of the same sort of reflectivity or temperature should give the same answer. Image quality, so modulation transfer is 0.3 at Nyquist. That sort of basically says, you know, to what spatial frequency can I see before I get aliasing effects. Geolocation accuracy is sub-pixel, so about 100 meters at nadir. Polarization less than 5% for the solar, 11% for the thermal, and channel co-registration better than 80% for all channels. So that is that individual channels really are looking at the same point on the ground, so we don't get geophysical noise within 1D bar retrievals. So I'll just quickly skip over this slide because it's just quickly how we will validate against requirements, but we would use bias error and stability using simultaneous nadir overpasses with other missions, and then looking at vicarious calibration with pseudo invariance sites. So this is what we would do during commissioning. We'd look at the noise statistics from calibration targets for the radiometric noise. We will have radiance profiles and saturation checks to look at dynamic ranges. And the other homogeneity requirements, again, they will be done looking at either vicarious calibration, cross-calibration with other pre-calibrated or pre-operational missions, looking at visual inspection of uniform images, and then maybe if we get the chance to compare spectral response, particularly in some of the absorption channels with other missions, that would also be quite useful. But to move on to the METimage calibration. So we have a thermal calibration device. So METimage works using a 2-point fixed point calibration scheme. So we measure a cold target of a known temperature, a warm target of a known temperature, and then we have 2 fixed points where we can then interpolate between. And the thermal calibration is performed once per scan using a warm black body and cold space. And on this figure on the right, you can see there, you've seen the scan profile on a previous slide, but there you see it's the space view. There's the warm black body, and on this aperture, sort of plus 120 degrees, is the solar calibration. Solar calibration is done once per day over the South Pole. We have a solar diffuser, which effectively the instrument can't look directly at the sun, but the diffuser plate is like a sort of diffuse white plate where it completely scatters the light and then comes into the instrument. And thereby knowing what the BRDF, the reflection properties of the diffuser are, then we can and we know what the sun's spectral distribution is, then we can then calibrate the instrument relative to the sun. Unfortunately, these solar diffusers, they're white, but they have a habit of degrading in orbit due to the UV light. So especially down at the blue end, they start to yellow a little bit. So we have another diffuser on board, which comes out roughly once a month, is sort of to be determined during commissioning. And here, this monitor diffuser will then measure the degradation of the nominal diffuser that we use every day in orbit. And then offline, we will have various calibration and diagnostic procedures, such as if we have an instrument mode change, we might have to look at diagnostic modes for looking at how the detectors are performing, or redoing a non-linearity correction. So we assume linear response, but actually it's not quite linear, and there are a few tweaks that have to be done to the non-linearity. And these can all lead to updates of the calibration key data. And last slide is just to give you a quick walk through the processing. So we have the level 1 processing. So the scene is measured. The raw data comes into the instrument in counts. Now on board, there is a little bit of processing done for the detector handling. So the instrument has a few masks where it knows where a few bad detector pixels are and excludes those from the data. The data then comes down. The first procedure we do in the level 1 is a non-linearity correction. So we have a set of polynomial coefficients where the idea here is that then we linearize the slight non-linear effects of the detector. We then have an offset correction, which then sort of brings the counts back down. It takes into account any sort of dark current and background current that might be present in the signal. We then perform a stray light correction, and then we do the gain calibration. So this is the part, so all these bits in yellow, these are artifact corrections. The grey bits are sort of more detector-based technical corrections that are carried out on board on the instrument before the data comes down. And then the crux of the calibration, so the conversion from counts to radiances, happens here with a gain calibration. So this is where we use our black body and solar diffuser. The geolocation is then performed, so we have a line of sight model for the instrument, and then this is where we locate the pixels onto the Earth's surface, in particular onto the WGS84 ellipsoid, and then we use a digital elevation model to also ortho-rectify the data. We then also within our geolocation check for sunglint 2, and then we end up outputting the calibrated level 1B radiances. So I think I've gone over on time a bit, but that's it. Thank you for listening, and if there are any questions, I'd be happy to take them.
Thanks, Pepe. I'd bring up the questions actually. Let me see.
It's question time now, isn't it?
Yes, it is question time.
Okay.
You can hear me, right?
I can hear you, yes.
Okay, now I need to grab this. Oh, I need to grab the screen and get the questions now. Okay. Pepe, the questions for you. VIRS was launched 10 years ago and succeeds in constraining the pixel growth.
So the thing with, I'll answer the top one. So from Martin first. Yeah, there was the pixel growth for factor 2 comes because there is a pixel aggregation scheme on VIRS where the idea you use the full sort of detector as you use merged pixels from the detector, and then as you scan out, you then separate them depending on what part of the swath you're in. But of course, with every change in the number of pixels you use for a given signal, you have a change in the radiometric noise. So obviously, the more detectors you use, the lower noises. So it's a trade-off of imagery and also having jumps in the spectral noise. In the noise as you go across the swath, I think. And yes, we could have implemented this, but actually our users didn't want it. They wanted to have the constant detector usage across the swath. So it was a trade-off effectively. But we have, VIS has some imagery bands at 370 nanometers at nadir. We have 500 meters uniform. So it's effectively just a simpler solution. It has generally for the moderate imaging channels that are on VIS, we are 500 nanometers rather than 750. We don't have the specific imagery channels, but we do have the constant noise performances across the swath. So it kind of depends on the end user. Some would rather the VIS implementation with the pixel aggregation, and others prefer the non-pixel aggregation. So, yeah.
Okay.
Next,
do you have a channel compare table of FCI and METimage?
Well, we can provide one, I guess.
Yeah, I think we have one. We have one comparing all the images actually.
Yeah. So
it's fine. We can provide trick there.
We will provide something there, I guess. Yeah, our famous channel numbering schemes, the next one. Right, this comes from originally the wish list of the METimage users was a plethora of 40 channels, which of course we had to have a feasibility analysis and there was a trade-off. And when we were going through this with METimage industry, we didn't keep changing the channels. We had to keep the fixed channels so the industry knows which ones we're talking about from the original 40. And they stuck. So at the moment, we are still with this sort of numbering scheme that has heritage to the original sort of 40 channels. But at some point, I suspect we might rename them. But at the moment, they're staying like this because we can't change it because it goes through the whole development chain of the instrument at the moment. So every single contractor, subcontractor, and that would have to change all their specs and documents. It's just not possible at the moment. Next one, will there be direct broadcast? Yes, of course. So we will have the same X-band transmission. So users with the receiver and the local area processor will be able to pick up the METimage data via direct broadcast.
I think we have an ICD document that is available publicly that broadcast users. We can also give links to that, and maybe, but I have to admit that there are updates going on in that direction. So, when it gets updated, we'll provide information to this.
The next question with 3MI and VI, yeah, we work together. So we obviously try and have synergy as much as possible. We have similar channels. I mean, they're on the same platform and look at the same areas on ground at roughly the same times. And we've already been looking at synergy between the missions. So looking at using the polarized channels to sort of analyze polarization sensitivity effects in VII. You have obviously the different path lengths through the atmosphere. So you could use the 3MI to do a more, say, detailed atmospheric correction where you have multiple path lengths through the atmosphere. Yeah, so that, especially when it comes to clouds and aerosols, I think there'll be quite a lot we can do between the 3MI and the VII and have some. There is also a multi-mission aerosol product, I think, planned for the two as well. So there will definitely be a lot of overlap and synergy there. It's quite a powerful thing, I think, having the 3MI and VI on the same platform. You say because you have the high spatial resolution with METimage to do the sort of specific cloud detection, but then you have an instrument with multiple views and multiple polarization effects also there with data at the same time. I think that's going to be very, very good. So yeah. Which applications benefit using VIS and METimage combined? Okay, it's just my feeling, but I think VIS has its strengths really with you have a lot of atmospheric clearing channels. You have the day-night band. You have the high spatial resolution imaging channels, and METimage you have a bit more with the atmospheric channels. But the problem is that they are not. You're not measuring the atmosphere and the surface at the same time. So you can't really use them in synergy because you'll have to wait too long for the next one to come over, I think. But yeah, the fact that one is, I think, more geared to like METimage's perhaps got a little bit more with the cloud top height and the water vapor, then perhaps with a combination of the two, you may be able to resolve a few things more. But in terms of using them together, I'm not sure you can directly use them together.
I think one application that comes to my mind, maybe Natasha shows this in her presentation, is also maybe related to the nowcasting at high latitudes, actually. So because with vias in METimage, you get
okay, so with the refresh rate, of course, but that's not, you could have the same instrument, it could be all METimage or more vias, and that would help the high nowcasting at high latitudes. It's not specifically vias METimage together that does. It's just lucky that you've got the number of instruments there, I think more.
Yeah, okay.
So the next one, the dual gain, I don't actually know. I've got a feeling it's like 350K. But we don't have dual gain. It's only a single channel at 3.9K, and I think the saturation temperature is, I don't know, it's on the slide that you can see what the maximum of the dynamic range is. But of course, it will depend on the fire. The difficulty with fire is that if it's a big fire, then the pixel saturates immediately. But if it's a small fire, then of course you've got a mixture of a very hot spot and then a diffuse area around it, and you can detect it. So,
okay.
Next one, I have no clue.
I again,
answer to that.
Again, I can maybe take this up. I think, I mean, this is also, if this document that is already released, there are some requirements there, but I think this is an upcoming document from what I know. So this has to be released for the users to get this requirements, minimum requirements necessary. So this is not it ready, or it's being updated. That's what I can say. That's the information that I have. I saw the question and tried to do some background information gathering. Okay.
For this one, there's a presentation exactly on this tomorrow, but essentially you have a channel in an absorption band which is sensitive, so like how much atmosphere there is between the cloud and the satellite, and then you have the other channel outside the band which then sees the surface, and by comparing you can then work out exactly from the absorption what path length of the atmosphere it must have gone through, and then and then invert that to sort of roughly where the cloud was. So oh, hang on, that was answering the middle one. Sorry, I was answering anonymous there.
Okay,
so now the next one.
That's a very interesting question from Trygve.
Numbering channels.
Same numbering.
You mean, I assume this means to the rather ornate numbering scheme for the VII. Yeah, okay, at the moment it will confuse users, but if we change it now...
Meant to your earlier question, actually.
Yeah, it'll confuse industry, and we need industry on board for the minute to get the channels right and the instrument right. So perhaps at some point we will be able to change this, but for now we have to leave it for all the industrial partners. So it's part of it's difficult because it takes so long to build a single instrument, and so there is always things that have come from the beginning. For example, METimage didn't exist when we started designing the instrument and the mission, and then METimage came as an instrument to fulfill the requirements. So we have sort of now two names, but there's nothing you can do about that. It's just a manifestation of the fact that it takes so long to just define these instruments, that there's always remnants that have to stay fixed throughout the whole procedure that you just can't change. And then maybe after launch we can, or later on in the project when the instrument is built, we can think about maybe trying to make it a bit more user-friendly at least.
I think this question was answered, right?
Yeah, we've done that one. Again, watch tomorrow. Yeah. Brightness temperatures are not, but the conversion coefficients to get the brightness temperatures relatively easy are. So everything is in radiance, but if you want reflectance or brightness temperature, I talk about this in my next talk.
I think maybe the rest of the questions we take offline, or maybe in the end, because if we have some time, because otherwise I think you need a short break, right, Pepe? 2 minutes maybe to drink some water. A leg break for everyone for 2 minutes maybe.
Yeah, it's empty. Just 2 minutes then.
Yeah, 2 minutes.
I think Chang Yong wanted to clarify something
everyone
about
at 14. Sorry?
I think Chang Yong wanted to clarify something about VIS. Hang on, so VIS 7050. Yeah, okay. He wanted to just clarify about the pixel growth. That's quite useful. Just to, yeah. So the pixel growth is significantly reduced through this pixel aggregation in VIS, so which we don't have. Yeah. Thank you.
Okay, then there's only one more question. Maybe that's about the nowcasting SAF product generation.
Units of nowcasting SAF will be made by FCI transfers and on the image. But I don't know. I mean, the nowcasting SAF will certainly be working with METimage data. So
yeah.
Okay. So
thanks,
quick 2 minute break.
So
I'll fill up my glass. I'll be back.
We meet at 14:54 for your next talk. See you everyone in 2 minutes.
I'll be back straight away. 2 minutes, yeah?
Yes.
So I'm back whenever you want to restart.
Okay, Pepe.
I'll just perhaps get my presentation sorted.
Okay. I don't know. I don't see my. Oh, okay. I can at least. Cannot.
Shall we start?
Yes, we can start, Pepe.
Okay, let's get going. So video's back. Good. Share screen and great. So can you all see the presentation? Sorry, can you see
yes,
this?
Yes.
Yeah, all good. Okay, so I'll start. So I will now talk about the characteristics of the Level 1B data set, how to use the data, what test data sets we've released, the format of the data and the dissemination baseline. So I'll quickly introduce the level 1B data. Then I'll talk about what I think are the three main issues for users to need to know in order to use the data. And the first thing is the use of the author rectification, so the DEM data, conversion coefficients for reflectance and brightness temperature, and the use of the tie points. I'll then describe the test data sets, the format, description, and the dissemination baseline. So just to introduce the data. So the METimage products, level 1B, contain calibrated and geolocated radiances for each channel. The product format is in NetCDF4, following the CF, sort of the climate and forecasting conventions. And the level 1B operational products, or granules as we call them, contain data within a 1-minute processing window. Some of you will already have seen the test data that was released. That was released before we had formalized this 1-minute processing window. So the next test data set will follow this 1-minute processing window logic. So I will explain it in this presentation, even though it's not applicable to the test data we've released, but I think it's good to explain now so you know for future test data. So first thing is you'll have this huge long file name .nc, which is the standard ending for the NetCDF data. And essentially you'll see Germany and EUMETSAT Darmstadt, which is the processor site, the satellite, which is SGA1, which is the imaging sounding satellite. So that's the first satellites, the A group of satellites. VII is for the visible infrared imager, so the mission name. The 1B represents level 1B, so for the calibrated radiances. Can't remember what the C is, but anyway, the product generation time is here, sort of in year, month, day, and then time in hour, minute, seconds. It's a global product. I think the D here means dev. I believe it will be O or something like that for operational. But then the important thing I think for the users is the granule start time and the granule end time. So again, same date time format here, sort of you see. So this granule started at 8:43 and goes to 8:44. And we need this sort of processing window, because if you can imagine you have a ground segment and it has to process data from all different instruments, it needs a sort of granules within fixed chunks. But of course, all these instruments have different scanning speed, and we want a whole number of products within each window. So effectively for METimage, we have a scan period of 1.728 seconds. So this means that there'll be either 34 or 35 scans of data per product. And exactly which we have will depend on the phasing of the scan start time with respect to the granule window. And I have a little picture for this in a minute on the next slide. But to note that the test data V1, the level 1B test data that has been released to users, is in these 5-minute granules. So again, the release of this test data preceded the consolidation of the sort of ground segment processing window size. So as I said, the next version will probably be compatible with this 1-minute processing window. So just to highlight what's going on, so you have these fixed processing windows, which I've highlighted on the left with fixed widths, but of course it's just schematic here. I've done it with sort of 4 and 3 lines, but you can imagine it's in reality it's 34 and 35. But what defines which window the scan goes in is its start time. So if its start time falls after the start time of the processor, it's in that window in the 1-minute processing. And you can see here, this scan belongs to this one. This scan in blue belongs to the second processing window. And of course, there comes a point where the phasing of the first is so far behind that the next one, the fourth one, falls into the next window. So this is why you end up with every sort of third or fourth product with only 34 scans versus 35. Now, the key thing in the data is the measurement data group. So we said that we have the NetCDF group structure. I'll come on to the structure of the whole product later, but just to get started with the bit that's the most interesting. So the measurement data consists of calibrated radiances in full resolution, sort of 2-byte integers, and then geolocation in tie point resolution. Now, the idea of these tie points is to save data rate, because METimage has so many pixels and so many channels. We've got to get the whole lot back down to earth and processed in a specific time. We have also, temporal requirements as well as spatial resolution and spectral requirements and everything else. So our sort of way around that is with geolocation data, it has to have a certain accuracy. You see with the radiances, if you're clever and use scale factors and offsets, you can get it down to 2-byte integers. But for the latitudes and longitudes, we can't do that. So they need the full 4-byte integers. So what we do is subsample the data. And I'll talk more about this in some slides later. But essentially, latitude, longitude, solar zenith, solar azimuth, observation zenith, and observation azimuth are all using this tie point scenarios, this scheme. We have the orthorectified latitude and longitude in full resolution, but they are somehow compressed into a short integer, because actually what they are is the difference between the orthorectified and the WGS84. So, and I'll talk about that later, how that works. But they are in full resolution because obviously you can't interpolate between, there's no regular, the land profile is not regular, and that's the whole point. So this is why it has to be in full resolution, whereas the WGS84 spheroid is much more continuous and flat, at least at a local level anyway. So these data are stored as integers and can be unpacked to their floating point values using the scale factor and offset. And all this is described in more detail in the actual product format specification. And just on the right, here's just a quick, I've just done a screenshot of the measurement data group opened in HDF view, and you have here the delta lat NDEM and the delta long NDEM. DEM stands for digital elevation model. These are the distances in north and east directions of the actual points on the Earth's surface, orthorectified ones with respect to the WGS84, and you would use these in combination with the latitudes and longitudes to then get the full resolution expanded digital elevation model version of the geolocations. So unfortunately, HDF these are actually dimensions. It shouldn't really be giving these as variables or groups, but we have the observational zenith, the satellite attitude, we have the satellite sub-satellite point, the scan start time. So the scan start time is a floating point. It's not an integer, and that is the actual acquisition time of the first pixel, the start of the acquisition of the first pixel of the scan. And then we have the solar azimuth and zenith, and then in the product, so all those of you who hate the channel numbering scheme will be pleased to hear that actually in the product we use the wavelength, which I prefer as well, because I can never remember which channel is which either. So 10.6, that's 10.69 microns, 12.02. It's come out in HDF view in sort of alphabetical order, but then that's the 1.24, and as you would then scroll down, you would see then all the other channels. So the delta lat NDEM and the delta long EDEM. So these are our sort of way of being able to get to the users the orthorectified data and the tie point data. So both options, but without blowing up the downlink. So effectively, what we do is we have the orthorectified latitude and longitude are given by the original longitude and latitude. So these are on the WGS84 spheroid. These are the ones in the tie point. So effectively, a user would have to expand the tie points, get the WGS84 latitudes and longitudes on the Earth's ellipsoids, and then apply the delta lat long in order to get the orthorectified, so the DEM, the digital elevation model corrected versions of the latitude and longitude. And essentially, this procedure is defined in the product format specification, but it essentially revolves around the fact that we calculate the arc length. Effectively, the delta lat and the delta long are the arc lengths of the angle subtended at the Earth's surface, alpha E and alpha N, and effectively these can then just be added to the WGS84 values in order to get the orthorectified values. And that can be done using these formulas here. It's relatively simple. So these is the delta lat, delta long EDEM and delta lat NDEM. You can then, using the Earth radius and the actual long latitude, get the angle subtended at the Earth's surface, the Earth's center, and then add them to the latitude and longitude on the WGS84, and then obtain the orthorectified values. And we wanted to simplify this for the users. Effectively, R technically should be the local Earth radius, but we've used a fixed Earth radius because it makes everything computationally much more simple. If the ground processor uses 600 fixed Earth radius and the users use a 3 fixed Earth radius to reconstruct the data, you end up with the same numbers. What changes very, very minorly is the values of the delta lat long values, but they are kind of not useful in their own right anyway. Until you've combined them with the latitudes and longitudes, they essentially don't mean anything anyway. So as long as the same radius is used at ground segment and at user end, then we end up with the correct orthorectified data. And just to show here's a bit of a pictorial representation of it. Effectively, if you have higher land, so here, if this was the flat Earth or the WGS-84 spheroid here, the line of sight from the instrument would come down to the ground here. What effectively the mountains do is truncate that line of sight a bit earlier. So effectively, the orthorectification moves then the geolocations towards nadir proportionally to the height of the land effectively. And so this is what this correction would enable you to do. And for the surface elevation, we use the Copernicus digital elevation model with 9 arcsecond resolution pole to pole, which is great because previously we were sort of using ACE2 where we have the good resolution between plus minus 50 degrees, but at the poles, you know, all the DEMs were a bit of a sort of mismatch of local DEMs to get, we only had really the 30 arcsecond global digital elevation model. So now that we have this Copernicus CanDNX sort of DEM, it's great. We have now this 9 arcsecond resolution for the full globe poles included. So the calibration data, okay, it's a bit unfortunate. It's called calibration data, but actually this group contains really conversion coefficients in the ISRFs. It does not contain the radiometric calibration coefficients themselves. These are used in the level 1 processor and have already been applied for the radiance, for the counts to radiance conversion. So the calibration data contains, the group actually contains the channel ISRF, so the spectral response functions normalized to their maximum, and the radiance to reflection conversion coefficients using the band average solar irradiance. The solar zenith and Earth Sun ratio can be found in the measurement data and satellite groups respectively. So if this is taken straight from the product format specification, but the calibration coefficient or the conversion coefficient that you would be looking for here in the data would be this E sun, and that would be in this calibration data group. And a similar analogy goes for the radiance to brightness temperature. Again, and this is taken from the format specification. You would need to extract these values here. In the current test data set we've released, these values aren't set, so quite a few users reported to us that how do we get brightness temperatures or reflectances out, and these values were not set. But in the next test data set that we will release, they will be set. And of course, you can always just look up what the solar irradiance and band average it for that channel based on the channel width if you want, because they're just heavy side functions at the moment, the ISRFs. Or another way, if you want to go to brightness temperature, you can just set A to 1 and B to 0, because there is, again, no spectral dependency in the test data yet. So coming on to tie points now, just to stress again this overlap region here. What you really have to appreciate is these 24 samples in the along track direction from scan to scan are very discontinuous. That you cannot then jump from this scan to this point in this scan and expect to have continuous data. It just doesn't work. In the along track direction, of course, we have constant scanning and pretty much continuous data, but we have this jump here in this overlap region at the swath edge. So data, as it would look if it was in full resolution, so you had latitude, longitude, these values in full resolution, they have 3,144 pixels in the across direction. So we have a numbering scheme from 0 to 3143. And in the along track direction per granule, you would have number of scans, which is this NL here, times 24, because each scan records simultaneously 24 lines, which would be this sample here. So it's 24 lines and then a certain number of scans. So each granule for the 1 minute windows would have 34, 35 scans times 24, which then would give you the number, this number here, n out, the number of lines in the along track direction. So that would be a full resolution product. Actually, what we use, as I mentioned before, is this tie point scheme. Now, I don't know, those of you that are familiar with the VIS compact SDR record, this is kind of a it uses that as a starting point, and then we try to simplify. So effectively, in collaboration with the METimage Science Advisory Group, we wanted to adopt a scheme where we could achieve this compression and get the latitudes and longitudes in a way that we were compliant with the data rate, but had at least pain at the user end as possible. So we've sort of found a compromise between number of tie points and an as simple as possible reconstruction scheme. So for METimage, we have tie points every 8 pixels. And what this allows us to do is to use a very simple sort of bilinear interpolation to then extract the full data. So if this is a chunk of data in a particular tie point zone anywhere in a swath, say, in this case, it's actually the first one, defined as the first one in the swath. So the red points here would be the tie points, and the purple points would be all the reconstructed individual data points to make up the full resolution data. And we have this coordinate system, which is again defined in the product format specification, where each pixel then where it would be in the tie point zone has its own little coordinates with respect to the tie points. So there are per scan, there are 4 tie points in the long track direction and 394 in the cross track direction. And what one has to really be aware of is, due to this bow tie effect, tie points are not continuous in the along track direction. So they are duplicated between the swaths. So if I go back 2 pictures, there will be a tie point here and a tie point here. But of course, this swath has to have its own tie point. So you can't assume the same tie point for the 2 different corners of the swaths, because they are in different places on the Earth's surface. So this is the complication. So if you look here now, I've tried to display 2 subsequent swaths. So this will be swath 1. The dotted lines in the middle are just to sort of get rid of the, show that it's a long swath, and we just missed out the middle bit of it here. So just start the start and the end. And here would be the second swath, and you can see clearly we have 2 separate tie points, because in reality this point is down here somewhere and this point is up here on the ground. So they overlap these parts of the swaths. In the middle they're fairly continuous, but at the ends there's overlap. And again, so the numbers in blue are the tie point zones, and in red are the actual tie points, and in purple is the full resolution data. So the important thing to notice is that you'll see here at the end we have this virtual tie point. So this doesn't actually correspond to a data point, but it's just used in order to get the last row or column of data, because we wanted to have the same scheme for every pixel. So it avoids then having to use an extrapolation scheme, same at the swath edge. So that you'll always, for every data point, you'll always have you'll always be within a tie point, a full tie point zone. You'll never have to extrapolate. You will always be able to interpolate. And as I mentioned, beware the tie points, say like tie points 3 naught and 4 naught. They are in completely different places on the Earth's surface because of this overlap. So the key message here is to always use the prescribed reconstruction given in the product format specification, and then it will work. So again, just to highlight here the how a product could look. And you have then the 394 tie points in the cross-track direction and 4 times the number of scans in the across-track direction, because there's 4 tie points per scan. And next thing is, for those of you who want to get rid of the overlapping regions, you can do that quite simply with this overlap mask, because some downstream level 2 applications need to know which pixels are duplicated to remove them, and then you leave continuous data at the swath edges without the overlaps. And in the level 1 product, we have I think it's in the measurement data, but in one of the flag sections, I think it's the pixel duplication mask. and it indicates to users which pixels are unique to a given scan, which ones also lie in a region that is sampled by the previous or following scan. So if you wanted continuous data, you would just go for the unique pixels, which would then have zeros for this mask. And this mask, as I said, is 24 long track pixels in the along track direction, 3,144 in the across track direction. So you would strip out the ones, and depending on how conservative you wanted to be about this, the twos are sort of variable and depends on the impact of the orbit height variation and the yaw steering mode being used at the time. And it may be that in practice we have no twos at all. The twos kind of stem from, originally we wanted to just have one mask per orbit, and there, as the orbit changes around the globe, you really do have a sort of plus or minus 1 pixel change in the overlap as you go around the orbit. But we now produce this mask per product. So per product, it's quite likely there won't be any variability across the product. So the chances are that I suspect these twos will probably disappear. So it will either be unique or not unique, and that will be it. And just to highlight what we really mean by the removal of the overlap regions, if you have swath 1 with the yellow and swath 2 with the red pixels, you can see here at the edge, it's highly exaggerated, but nevertheless, you see this sort of intermixed region. And after the application of the masks, you still have this discontinuity in the scan pattern. It's not like everything is then continuous. It's still a discontinuous pattern in terms of the shapes of the line. Like you see, they come together, but the pixels all stay belonging to each swath. So you remove this sort of oversampling. Of course, you can leave it there if you want it, but if you don't, you can remove it. So I'll now come on to the test data. So we released not so long ago a set of test data. These test data, the idea was to generate realistic top of the atmosphere radiances consistent with the observational geometries in METimage in support of the ground processor development. So what we wanted to do was have some top of the atmosphere radiances, sort of some test radiances that we could then feed into our instrument data simulator, which then takes into account the instrument model, the orbit, attitude and pointing model, and then generates satellite counts and level 0 data as if it was being measured by the instrument. So it introduces also all the instrument artifacts, noise, stray light. And then we have a METimage level 0, level 1 processor. It's a prototype processor, which then applies the level 1 processing and reverts back to the level 1B radiances. And so we sort of then model this full chain. And these simulated top of the atmosphere radiances were generated by Jerome Reedy's group at the University of Lille. And effectively, they took the instrument viewing geometries, orbits, and top of the atmosphere radiances, effectively using 3 orbits of AVHR data, which covered Africa and Europe, including summer, winter seasons. And these were selected as proxy for the orbit simulation and the extraction of the geophysical information. Now, of course, AVHR is limited in channels, and you think, okay, we have METimage, 20 channels, there's much more information that it will measure. So we needed some extra ancillary geophysical data to feed into the radiative transfer model. So such as MODIS surface albedo, we had MAC reanalysis and aerosols, ECMWF, atmospheric states, etc., to then generate the full state vectors for input into the radiative transfer code. So it's just a little schematic here of the actual simulator, and we had lots of databases of instrument and optical properties, and then of course databases for the scenes. And then the results were the radiances measured by the instrument as a function of channel, pixel, and viewing geometry. And there's a little link here to the study if you're interested to look at. So just to show you some of the results, so if we have, say for 670 nanometers channel, this is our favorite granule out of the lot over Greece and Italy. It's with some lovely cloud structures here. And so if this is the radiance histogram for the equivalent AVHR channel, this is, sorry, at the bottom is the AVHR radiance histogram for this scene, and above is the simulated one for the METimage channel. So you can see the comparison there. So in that test data set, we distributed 6 granules of 5 minutes, and each 5 minutes has 175 scans, and the ground track at sub-satellite point is illustrated here in this figure. So that was the ground track of this test data set, and it consisted of 2 nighttime granules, 2 twilight granules, and 2 daytime granules. But it was an initial data set, so to think of it really as a prototype, look at the format, the radiances, but it's really a precursor to the sort of complete data set. There's various, the scope of this data was indeed limited. I'll go through, the limitations here. So there's no there was no digital elevation model applied, so there's no orthorectification. So all the latitudes and longitudes are on the WGS84 spheroid. There's no height of the land taken into account. That means these delta lat dem, ndem, and delta lat edem fields are not filled at all. And since the instrument does not fly over the South Pole during this test data quarter orbit, there was no update of solar calibration coefficients performed at all. There was a little hiccup with the stray light handling, and it seems that it's still not even at instrument level consolidated yet, because it's one of these things that comes in progress with the instrument development. But effectively, the instrument data simulator simulated stray light, but the level 1 processor was not consistent with the simulator in terms of the correction. So there are some bias errors in some channels, which you might see some, if anyone has tried to make some color composites, some of them look a bit exotic, and that is because of this bias error due to the stray light. It's small and only present in some channels, but if, for example, colleagues who did cloud tests and retrievals would see thresholds not quite working, and as I said, it was visible in some of the color composites. The calibration coefficients were very simplistic, so there was no scan orbit dependency or temperature dependency. It was just fixed numbers. We did no landmark processing, so there's no flag set. And in fact, there's no quality control performed at all. It was all for nominal cases, and all flags in the level 1B quality product were set to nominal values. In the calibration data was empty, so there was no ISRF and no conversion parameters. Just to highlight that the test data is not in line with the operational baseline, which will be 1 minute processing windows. But so you have in this test data set 5 minute granules. And for the solar channels, the day-night transition is a bit odd. It's like just a straight line across the swath. It's just based on the illumination conditions at the sub-satellite point, and then applied just point blank to the entire swath. But for the next data set, it'll be done per pixel. And the next data set V2 will improve on V1, and will use the 1 minute processing windows, and it will include 3 orbits of data, not just half and not quarter of an orbit. And just here's some pretty pictures. So I think this is actually for the which channel? Oh yeah, the 11 micron channel. So that's just the full. That's what went in. Sorry, no, this is what went in terms of top of the atmosphere radiances into the instrument data simulator. This is what came out from the prototype processor at level 1B, and these were the percentage errors. So this was one channel that was not affected by the stray light problem. The ones where there was a stray light problem, you see a bias, which can be anything between sort of 1-2%. So if you see these bias errors in the test data, that's what it's from. And come back. And this is the famous granule over Italy and Greece, which is not in the test data set that has been released, but will come in the next one. So that is the first granule of the first orbit of what will be test data V2. And just quickly, the format specification. So for EPS-SG, the way it works, we have a generic format specification. So this defines the conventions for naming, the format, the metadata for all products in the ground segment. And the native format for everything is NetCGF4. And then we have specific format specifications for each product generation function. And for each product generation function, we have a format spec. So there's one product generation function for each product, imaginatively enough, so that for METimage level 1B, there's just one PFS. For level 2, there's one for the clouds and one for the OCA product. And then for different instruments, again, it depends on the number of products. But effectively, you can refer to the GPFS for all the generic things and namings and formats, and then for the specific PFS for the actual instrument structure and the variables. And there's a link here at the bottom of the page to the METimage one. And every EPS product looks like this. So you have a root directory and with some global attributes, global dimensions, and global variables. Essentially, you have three main groups. A status group, which will tell you everything about the satellite, the orbit, the instrument, processing, so what processor version, what format spec, all these things are included here. The next one is the main group, which is of most use to most users, which contains the actual data. So we have the measurement data group, which I've already described in some detail at the beginning of this talk, and the calibration data group, which contains the conversion coefficient. So these two we've kind of covered already. Quality information will tell you a little bit about how the processing went in terms of calibration and geolocation, like were there any irregularities, did anything fail, or was anything degraded? And same with the processing flags, it sort of gives you a summary, was there any missing data, did we have any saturation, any sunglint, things like that. And sometimes we have some group dimensions, group variables, and group attributes. Mostly in this group, we have group dimensions. So things like number of scans or the number of across-track pixels, things like that, they're common to all these groups. So anything where it's common, they go in these group variables here. And the last one, the quality statistics, this is more for just an overall statistical view of the product, like how much product do we have? Is there any missing data? Were there any satellite maneuvers at the time? So it's just a sort of top end, look first. So, in order to get the sort of overall picture, you can look at the quality statistics to see, is my data actually there, for starters? And then you can go into the detailed quality information in the product. And just to, I've already talked about my next slide, but just to go through it again, you have the data, which has some group dimensions as like number of channels, calibration data with the conversion coefficients, the ISRFs, the radiances and geolocation parameters, and the measurement data, quality information concerning how the calibration and geolocation went, and then processing flags to indicate any missing data, saturation, sunglint problems encountered during the processing. And here's what I wanted to show with the flags. Generally, I've just taken this one random from the format spec. Data quality is randomly, it's always a value 0, it means that everything is okay. And we set individual bits to indicate different problems. So if a value is not 0, you need to then see which bit was set. So from the end value, you can tell which bit's set. And then you can see if it's radiometric calibration, degraded or failed, or if there's something wrong with the geolocation. And you see that here. And last but not least, the dissemination. It's one of these. Hang on, let me just get it all up. Right, okay. So data comes to EUMETSAT, and we have basically as baseline for the global product for METimage, we have near real-time dissemination via EUMETcast, so satellite and terrestrial for both global and regional products. And the latency is 70 minutes for the global, 30 minutes for the regional currently. And then we have near real-time dissemination that will also be available. So 24 hours for level 1, 40 minutes for the auxiliary data. So that's calibration, solar calibration coefficients that might be needed or something like that for direct broadcast. And then that would also apply to the archive. So that would come under non-real-time dissemination. And I think that's it. So that's just on the right-hand side, this box here is just the main summary. So you can see METimage here. This actually slide gives you the whole dissemination baseline for EPS-SG, but for METimage specifically, this is on the right-hand side how it is. And the data size is about 8 gigabytes per orbit. And I think that's it.
Well, thanks.
Yeah.
I mean, really great presentation, actually, especially considering that, these are very, very important for the users to know how to do this, actually, because very practical, I would say. I mean, thanks for the effort, Pepe.
Yeah, we try to make it as useful and easy as possible for the users, but there are always trade-offs that we have to make in order to get things downlinked and compressed. And so,
yeah,
this is what we try to do, especially with the tie points, is to keep, the author rectification and the tie points as simple as possible. So, yeah. I
mean, also in addition to the PFS for VIA, we also released the GPFS online. So on the EPS-SG test data page, you will get the PFSs as well as the GPFS also. It's possible to get them. When we send the responses back, we can add these links to the document and provide them to everyone. Can you see the question?
I can see the question, so I'll start with the top. Author rectification does not do cloud parallax. It's really just the surface underneath. So it's according to the digital elevation model. Mm-hmm. So at the time we do that, we actually know nothing about where the clouds are. That comes later in the processing. That's a good question.
Okay, thank you. And I think this is comment from Adam that the nowcasting SAF will provide obviously products from both MTG and EPS-SG, so both FCI and METimage. I think that can. Yeah. Okay, do you want to say something?
Test data version 2, I'm working on it. It's keeping me busy.
It's sometime Q1 2022, if I remember, or maybe later than that. But next year, early next year is when test data version 2.
Compression. Okay, what we've actually done is there's the scale factors and the offsets for the data are selected in a way that we don't store noise. So we've chosen a size of a product, size of a 4x, 2x, and then use the scale factor and offset so it fills the minimum space without storing noise. So we don't fill the whole number of bits. So that actually is paving the way to compression, if you see what I mean. So all those bits then that are not needed because you would then just be storing noise because the instrument, it's like within the instrument signal to noise ratio or something like that, are then free and they could be compressed in the future. But until we have finalized exactly what these scale factors and offset needs to be in the dynamic range and how many bits we have from the instrument and various things like that, we can't address compression yet, but we are proceeding in a direction where we only fill bits where we need to, and then any bits left empty can automatically be compressed very straightforward. And then the information, whether we can use some sort of, I don't know, other compression in the imagery, we will see. So that's where we are. So it's likely there will be some compression applied at some point, and but we just don't have it yet. We're not as far ahead as, say, with FCI.
Okay.
So
I think we need to move a bit quick because we are a bit late.
FCI use WXX. Don't know actually the answer to that one, but I would have thought DE makes more sense if it's produced in Germany. XX might just be a placeholder. So maximum file length is an excessive less than 255. So do I, because my processor falls over on 255 characters.
I think it's less than 255.
I have that bug already. So yes, it will be what it is, but yes, we hope so too.
The details are there in the
worst is if
it's less than.
Where I've got into trouble is when the path length is included in the file name, and then you have have it stored in a parameter that's like 1 byte, and then it goes completely overboard. So, if in doubt, separate it from the path.
Sorry, I don't know.
So anyway,
okay. Mm-hmm.
Should we answer the other questions offline then?
I think we can quickly go through that. I think if just quick, I think one is a comment from Adam that it's nice to see the type point scheme used.
Yeah.
So I think you also mentioned that.
Adam, I didn't want to reinvent the wheel, but I've tried to make it a bit simpler. That's all I've done. So I've used more tie points, so the actual then extraction is a bit easier. So it's so you don't have to do so much. But
what about his next question? You can take a minute to answer that, because we also.
So I suppose this cross-canal dependency. No, not really. Actually, for the local area processor, it should be able to scan for scan. So you wouldn't know. Well, no, you would have to wait for the processor works swath by swath. You can't process individual individual pixels independently, because you need the calibration target count. So, and that's only once per scan. But there won't be any inter-swath dependencies. So you should be able to process relatively one swath. You might need the previous swath just to have some interpolation between the calibration target counts and the dark view, but it shouldn't be. There should be no straight line algorithm that needs then 50 lines or something similar like that.
Okay. Okay, Pepe, thank you very much. I think we still, Dovia, I mean, I think it was good to answer all the questions, because yeah, they're fairly very relevant. We will have a break now for 2 minutes again before we start with Andre's SatPy Reader and SIF demo. So before that, let me also tell you that we are interested in hearing your feedback about this webinar, especially for session today. There will be a link in the chat coming up now where you can express your opinion about today's sessions. Thank you very much. So we meet at 15:39. Thank you.
SatPy is responsible for reading and generating products out of the acquired satellite data. So SatPy supports both GEO and LEO products in many input formats. It can read many output formats as well. It has a lot of built-in composites and RGB recipes that can be used right away. It can be used to resample data, basically to any projection that is available in the Proj library, and much more. It can really do a lot of interesting things with data. And all packages in Pytrol are free and open source. So you're welcome to look at the code. It's hosted on GitHub, so you can just take it and use it. If you feel like you want to contribute, add your own feature, comment on the code, feel free to get in touch and contribute to the project. Okay, so the first and I would say only thing that you need to do to use SatPy is to install it. You can use Conda or pip. So pip install SatPy introduces my demo. So I will just quickly go to my IDE. So I prepared a little code snippet that does the basic operation of opening a channel from VII data and resample it. And I will run this now line by line and give some comment of what's happening in the background. So just follow the code execution. And as every other Python code, it starts with the imports. From SatPy, it's actually just one. We just need a scene object where we will load and store all our data that we are going to read from the files. I'm then just gonna import a couple of more packages to find the files in my system. And yeah, the first step is to tell SatPy where to find my data on my computer. So I have a folder with a few granules of VII that I'm gonna pass into the scene object. So here we are initializing the scene. All it needs is a list of file names. So here I'm using the glob library to get the list of all netcdf files that I have inside my folder. And the second argument that we need for the scene is the reader. So just define which reader you want to use to open the data. In this case, it's self-explanatory. It's called VAI_lev1b_NC for netcdf. So I'm just going to execute this line. And now SatPy in the background is opening and looking into the files that I've provided, trying to figure out what's in there, what can be done with them, and initialize the whole process. So if I just switch quickly to my console, we can explore what SatPy has found out about the files and what can be loaded. For example, by just calling on the scene object the available dataset names method. And this one will give us the list of everything that can be loaded from the files that we have produced, that we have given to SatPy. So we have all the geolocation, latitude and longitude arrays that we have just seen explained by Pepe. We also have the observation and solar angles. And then finally, the whole list of all channels that are inside the files. And they are called as inside the files, so by the wavelength. So basically, everything that is listed here can be directly loaded through the scene object. So let's just do that. Let's just take the first channels, 10.69 micron channels, and put it into the load call. So I'm just going to execute this line. And now SatPy is taking the files and extracting the channels that we have provided. So with the show, we can just look at what has been loaded. And there you go. We get the swath image. Of course, now it's still in the swath acquisition geometry since we just read it from the file. But yeah, as we saw in basically 2 or 3 lines of code, we opened the file, we loaded a channel, SatPy performed the calibration. So what you're seeing here is actually brightness temperatures already. It computed the latitude and longitude for the whole array using the tie points, everything automatically in the background. But yeah, so now we have the data in swath geometry. So to make it more useful, we can resample it to an area that we know. So for that, there is a simple call again onto the scene object, which is called resample. And all it basically needs is the area that you want to resample your data onto. There's a whole list of areas that you can use that are built in SatPy, but it's very easy also to create your own region of interest in the projection that you are more comfortable with. I'm using here just an area above Europe. So I'm calling the resampling. Since I didn't define the resampling algorithm, it's using nearest neighbor in the background. But again, there are a list of available algorithms that you can use depending on the specific application that you want to have. Okay, then finally, now we have resampled the data. I could show it again, but let's just save it to a picture, to a file. So on the resampled scene, I call save dataset. I provide the channel name that we have been looking at until now, the output file name. So in this case, I'm producing a TIFF, actually a GeoTIFF. And as an optional, I also give the overlay argument so that I can overlay coastlines on top of my image to help the visualization. For that, I just provide the folder to the shapefiles of my shorelines. You can find them easily on the internet. So let's just execute this line. It's taking a couple of seconds. And there There you go, it's finished. So I will just go to the folder. There you go, it created a fresh VAI image. So I quickly open it. And we see the resampled swath on top of Europe with the coastlines added. And yeah, of course, what I've shown you here is just an appetizer. You can do a lot more things. You can create composites. You can tune what you want to load. You can change the calibration. You can do a lot of things. So I just invite you to take a look at the documentation and try it out yourself if you think that this could be interesting for your workflow. Okay, so I am opening again my presentation since we are going to continue now with a quick demo of SIFT. What is SIFT? SIFT is basically a visualization software for satellite data. So it has a graphical user interface, so you can just use it as a normal software, so to say. It is originally developed at the University of Wisconsin at the Space Science and Engineering Center. And it is also free and open source. So you can get the code, you can use it, you can modify it freely. And of course, you are also very welcome to contribute. And EUMETSAT is developing currently a new version of SIFT. And we are tailoring it for the needs of the new MTG program. So specifically, we are improving the interface to Spectral. So actually SIFT in the background, in the backend, is using SatPy and other Spectral packages for loading and modifying the data. And we are tailoring SIFT to visualize geo and as well LEO data with integrated resampling. There will be the possibility of visualize point data. And we're also looking into an automatic update mode where SIFT monitors continuously a folder and automatically loads a new chunk or a new granule when it shows up in your monitored folder. So I would, again, just quickly give you a demo of SIFT to see it in action. It's written in Python again, so I can just call it as a Python module. There you go, it's fired up. And I will just say propose to just load some VAI data again. First, I'm going to change the projection. We want to load the data in the first place into. I'm just using a Platic array projection here. So to load data, I go to the Open File Wizard. And it will ask me which reader I'm using again. So here I select the VII netcdf reader. And I am gonna browse to the folder with my data. Here I have about half an hour worth of VII granules. So I'm gonna load all of them. And now it's trying to figure out again using SatPy what can be loaded out of all the granules that I have provided. So we get again the list of data sets that are inside the files. So I select the VII 10.69 micron channel in the brightness temperature calibration. And up here you can modify or you can select the resampling method. There are always a few available. And the radius of influence for your search and resampling algorithm. So by clicking finish, I'm sending a command to SIFT and then basically to SatPy to open all the files and retrieve my channel. This is gonna take a few seconds. Again, we are loading quite a number of granules. And once the data is loaded, the visualization is actually extremely fast since SIFT uses GPU acceleration if available, so that as you will see in a second, the panning and zooming is basically immediate. and the tiling and the visualization of the data is basically immediate. So as you see, I'm just scrolling through the image, and it's fully smooth. Yeah, and so what can you do with the data now that it's loaded? A nice feature is the point probe. So you can just click here on the point probe and click around, and you will see the value of the layer of the channel that you have just loaded. And if you like to explore an area, you can also click on a region and define your region of interest with a polygon. And by clicking on area probe graphs, you will get the histogram of the area, of the values of inside the area that we have just defined. And by moving the point, you can even see where inside your histogram you are moving on each pixel. And yeah, another nice feature, for example, is to you can change the color map if you like. So by that, just a right click to change color map will give you the possibility of changing the limits of your color map, but also changing the type. And there is a whole list of available color maps that can be chosen, some specific for specific channels. So for example, by selecting the IR clouds winter, I get something like the IR colorized clouds and the sandwich image. A nice feature, again, is to change the projection. It can be done on the fly by just clicking here. So you can define your own area. Here we have some full disks from MSG and FCI. So if I just select an FCI area, the reprojection is basically immediate, and the scrolling of the data is completely smooth. So of course, at this point, you could also load into SIFT a full disk of FCI and just do the comparison and the overlay with Leo and geodata for your purposes. And yeah, I think that's the main features. These are the main features. If you're happy with the image you're looking at, of course, you can even export it. There is an export image button where you can select your setup. And if you load multiple granules or multiple orbits or multiple full disks for geodata, you can even have an animation running down here. So yeah, again, an appetizer. There are a few more features, and we are still working on this. So we will add a few more. And we are looking into the possibility of releasing the software to users so that you can also benefit from this development and use it for your own applications. So yeah, I think that's it for my part. Thank you very much.
Thanks, Andrea. That was great. Again, to hear the application, how to visualize the data. I mean, I for sure would love to use your SIFT. But I think, like you said, I mean, there's more to come, and this is only a trailer. Maybe in the next webinar, there will be more, or any next user interaction that happens. I think we should have a SIFT demo also, where maybe we can also get the users to work hands-on. You know, this is quite an interesting tool. Yep. What I will do is to see if you have any questions. Oh yes, there are a couple of them. Presenting full screen. Can I share? Oh, okay. I think that was a question for Pepe before. Can you read that for me? In addition to support MTG FCI, will EUMETSAT provide a SIFT version supporting the missions on EPS-SG?
Yes, basically, since SIFT is tied to SatPy, everything that SatPy can read, any Leo data that can be brought into a SatPy reader can be also used in SIFT. So the only thing that will need to be done is just to add a reader, and you can use it straight away also in SIFT.
So at the moment, VIA can be read through SatPy.
Exactly, yes.
We don't know about any other.
As far as I know, there is no other reader currently, but it's quite simple to add it. Again, if a user feels motivated, there are developing instructions on the SatPy documentation to guide you through how to build such a reader. And yeah, so this is very open.
Yeah, thank you. Is an RGB composer included in SIFT?
Yes, there is the possibility of composing RGBs, indeed. So you can load different channels. You can select which channels to put. You can even do algebraic calculations. Choose your limits. Basically, everything you need to build an RGB. I didn't demo it just for the sake of time, but there is a possibility. Yes.
Okay, and next question. I think I come back from full screen. Maybe that's better. Can you see the screen now?
I could see it before. Now I see the web page, the full web page.
Okay. Yeah, then that doesn't work. Okay, I was trying to do something actually clever, but it does. No, sorry about all this.
No problem. In the meanwhile, I read Garrett's question is about the overlap.
Okay, please.
The overlap of the pixels that we have just seen explained by Pepe. To be honest, I don't know. I will need to check inside the reader how it's implemented now. So there is, of course, the geotie point calculation and interpolation, but yeah, I will need to check this.
Okay. So Garrett, you will be contacted with the answer actually. Okay, I think we can Andrea make his sample SatPy code available and where?
Yes, we are looking into this. So the code is also in the slides. So when we release the slides, you will get it there. But we will probably also release or distribute the code either as a plain Python code or in a Jupyter notebook or Kaggle. We will look for a solution and let you know. But by the way, there are also examples on the Python and the SatPy documentation. So you can, they are very similar. So you can already start now if you're interested.
Thanks, Andrea.
Sure.
Thanks for the presentation and for the Q&A. I think we still can take a 2-minute break after this so that everyone gets a leg break. So we meet in 2 minutes again, 16:05. And also please take the time to respond to the poll, please. Thank you. This will help us to improve the next one. We have 3 more upcoming webinars. So this will be really helpful for us. Thank you. Hi, welcome back, everyone. So next we have Natasha Strelek-Mahovic talking on the heritage data, new channels, enhanced resolution, RGB evolution of METimage. Natasha?
Okay, good afternoon, everyone. I hope you see my screen well.
Yes, we do it. We
Very
do
good.
see it.
Very good. So as Shrika said, my name is Natasha Strelec-Mahovic. Together with my colleague Vesa Nitosvara, we are both user training officers at EUMETSAT. We prepared this overview of the novelties METimage will offer in weather-related applications. So we have heard from the previous presentations about METimage sensor, about its characteristics and format of the data. We saw from Pepe the whole palette of the new exciting products and applications, and many more we will see in tomorrow's presentations. So now what I will do here, I will dive into the world of imagery. We will look at the new channels in the RGB combinations, and we'll see how better spectral and spatial resolution will offer more exciting and useful imagery than those that we have available currently with METOP satellites. So just sorry, oops. Something happened to it, but okay. In the constellation with other polar orbiters, which will be carrying similar payload, for example, VIRS, METimage will enable additional slots in observing the Earth and the atmosphere. So actually what we will have here will be the additional, when METimage once replaces METOP-B, for example, it will offer images over the, especially over the polar areas and northern latitudes, which will be comparable to VIRS imagery, offering another slot of observation and enabling better observing of the Earth and the atmosphere, especially in the northern latitudes. So what we have also compared to METimage, compared to AVHRR, METimage will have many more channels. So it will have 20 channels compared to 5 channels that we have now on AVHRR. It will have enhanced spatial resolution. As we heard from Pepe, the channels will have 500-meter resolution compared with current 1 kilometer resolution. And what is even more important, much better spectral resolution. So we will have 9 channels that will be available on METimage that are currently not available on the AVHRR, and there are 6 more channels that are not available either on AVHRR or on VIRS. So we will have many new channels. As you can see here in this slide, there are the green channels are the ones that are not available currently either with VIRS or AVHRR. So this will be completely new observations from coming from the METimage. What is here important and what will be especially valuable for weather applications and for meteorological products will be the 0.9 micron channel and both 6.7 and 7.3 micron channels, which will provide information on water vapor in different layers of the atmosphere. That will improve the derivation also of the wind products. Also, what I could mention is 3.9 micron channel together with 4 micron channel that will be an important addition to VIRS, in particular for land and sea applications, for land and sea surface temperature measurements, and for fire-related applications. So with respect to spatial resolution, we will have a set 500-meter resolution with the METimage. So you can see here the comparison between 1 kilometer and 500-meter resolution image. This was taken by Aqua Modis instrument, and you can see clearly how the cloud top structures, for example, will be much better visible with 500-meter resolutions than with 1 kilometer resolution. What is especially important is even when we will have a new geostationary imager, FCI imager, Vesa yesterday nicely showed us all the products that will be available from the FCI for the weather applications, but still, even when FCI will have very good resolution in the areas close to the pole, we will still highly benefit from the METimage data and products because of the viewing geometry close to the limb of the geoimages, as it is clearly visible in these images, the precision of the measurements between geostationary and polar orbiting sensors is highly in favor of the polar orbiters in high latitude areas. Here I have a comparison from ABI sensor and VIIRS image at the same time and the same place, and you can see how more clear the polar image is. So these new channels that we saw in a few slides before, which are currently not available on AVIGRR, will enable RGB products which will be same as currently available from VIIRS or MODIS, and same to those that will be available from MTG FCI imager. So as the most important new RGBs, I would maybe emphasize cloud phase RGB, also cloud type RGB. So these are the two RGBs that will be especially important for meteorological applications, but there are of course many more, and I will shortly now elaborate on. If you're interested in looking at the new RGBs and what they will look like and what are the characteristics, you can go to EUMETRAIN webpage, where you have many RGB quick guides showing what the RGBs are composed from, which channels, and what they reveal from the meteorological information. So availability of 0.4 and 0.5 micron channel, which is currently not available with AVIGRR, will enable production of true color RGB images with 500 meter resolution, same as is now available with VIIRS. Here VIIRS is used to mimic the future METimage product. This RGB provides colors which are close to the naturally observed colors, and what you can see that surface features like vegetated areas, deserts, oceans, snow ice covered areas are easily identified with this RGB. On the other hand, this RGB does not clearly differentiate between cloud types, because it only differentiates clouds by their optical thickness. And it also does not differentiate between snow and clouds, but it can differentiate between different aerosol types, like for example dust, volcanic ash. This can be seen in the image, and also when you look at the water bodies, you will see that it can be very well distinguished water that is deep, clean water from the one that has some suspended matter or is shallow or has some algae bloom. So this can also be clearly seen in this image. So this is the true color RGB, which offers the, let's say, most natural view of the Earth, and this will be available with METimage. The other RGB, which will be very important for microphysical analysis of the clouds, is cloud phase RGB. This RGB uses a combination of 1.6 and 2.2 micron channel. It was presented already yesterday by Vesa. You have here a link to the cloud phase RGB quick guide if you're interested in more details. So since it uses both microphysical channels, 1.6 and 2.2, it will provide more reliable separation between ice and water clouds, and also separation between clouds with large droplets and clouds with smaller droplets. This can be very important for example, nowcasting applications. So you will be able to distinguish the whole range of different combinations of cloud top phase and particle size. And as I said, nowcasting application is probably the main application of this RGB. It is used for convection monitoring, since cloud top glaciation is well seen in the developing phase, and the presence of small particles on or about mature thunderstorm tops can be recognized with this RGB. It can be used as updraft intensity and possible severity of the storm. So this cloud phase RGB can be very useful in convection nowcasting. Besides application in cloud phase analysis, cloud phase RGB has proven to be very useful also in recognizing the type of snow on the ground. This we had in a recent case of very severe snow over Spain in January this year, where we could see the difference between fresh snow and snow in high altitudes, so in higher mountains, which is lighter because of the smaller crystal sizes, and the darker colors which are connected to the older, let's say older snow or melting snow due to larger particles. So cloud phase RGB will also be useful for snow analysis. The other important RGB will be cloud type RGB that will use the availability of 1.3 micron channel. This RGB combines cloud height with cloud phase and cloud optical depth information. It will therefore provide good color contrast between cloud types. You will be able to see thin cirrus clouds over other clouds and over cloud-free lands or sea. And also snow and ice on the ground will be clearly distinguished from high-level ice clouds. This RGB also enables detection of supercooled water clouds, which might be important in aviation applications. In case of deep moist convection, for example, the cloud type RGB discriminates between the thick and the thinner annual parts of the convective clouds, and it detects high and thin ice clouds in reddish colors, so much better than cloud phase RGB. Of course, due to use of 1.38 micron absorption channel. So another combination that uses 2.25 micron channel is the daytime snow RGB. This RGB was developed by colleagues in Meteo France, and as you can see in the same example as we saw from the cloud type RGB, the one that from the cloud phase RGB, the difference between fresh snow, which is here shown in yellow colors, fresh snow with smaller ice particles, and the older, let's say, larger particle snow in orange colors can be clearly seen. So this is also something that will be available with the new channels, and this new daytime RGB can also show daytime snow RGB can also show the temporal evolution of snow microphysics. So in this example, we can see how the snow color starts from yellow, and then with melting and it turns into reddish colors. It is also important to notice how with this RGB, it will be possible to see the snow below high thin clouds and also low thin clouds. So the snow will be visible on the ground even below the clouds. One of the channels that will be available and that will enable, in this case, dust or ash and also microphysical monitoring is the 8.5 micron channel, because in the combination with 12 and 10.7 micron channels, it will enable dust monitoring from EPS-SG. This will benefit especially in higher latitude regions, in which FCI imagery will have coarser resolution and higher scanning angle. So for dust monitoring in northern latitudes. This RGB enables monitoring of the formation and dissipation of fog, for example, and low stratus at high spatial resolution day and night. It has good performance for low cloud detection during winter at high latitudes, and also enables distinction of cloud particle phase and differentiation between ice and water clouds in this composite. So not only dust, but with the same combination of channels, only using different ranges of brightness temperature differences, will be used for volcanic ash monitoring. And here in this example, we have a VIRS volcanic ash product that shows the difference between ash cloud and ash cloud mixed with SO2 plume. So this is something that will be also available with METimage. So using the properties of 3.9 micron channel, which will also be new, the 3.9 micron channel is very sensitive to high temperatures, And therefore, using it in fire temperature RGB, it will enable identifying the most intense fires and differentiate these from let's say, cooler fires or not so intensive fires. Since from 3.9 micron to shorter wavelengths, background solar radiation and surface reflectance increases, fires need to be more intense in order to be detected, for example, in 2.2 and 1.6 micron bands, as more intense fires emit more radiation at this wavelength. So small or cooler fires will show up only at 3.9 micron channel, and therefore in fire temperature RGB there will be red, while more intense or hotter fires will have greater contribution of the other two channels, 1.6 and 2.2, and then they will the colors will vary from orange to white for the most intensive intense fires. Fire temperature RGB also reveals burn scars, so this will be a very important product for monitoring fires. Besides fire temperature RGB, availability of all the channels around 4 microns with other new channels will enable derivation of other products like fire radiative power. You will be able to monitor also burn scars, and so fire monitoring with METimage will definitely see its revolution in the next years. An important novelty in polar orbit imagery missions will be measuring in the absorption bands of the water vapor. METimage will provide the information about humidity content in different layers, which will enable deriving humidity profile used for both NWP and nowcasting applications. Yesterday, Vesa already showed an example of 0.9 micron channel from FCI. The same will be available with METimage. So there will be a 0.9 channel, which will be a novelty in both geostationary and polar orbit globally. And it will enable retrieving low-level humidity content, which is an important factor in convection nowcasting, for example. Together with other two water vapor channels, it will enable deriving water vapor profiles and total column precipitable water, important in particular for NWP and nowcasting applications. So altogether, if we look at the better spectral, better spatial resolution, new channels and RGBs, together with adding a satellite to an existing constellation, this will be particularly beneficial for high latitude areas. We can see here an example. Of convection monitoring over Finland with current AVHRR, which will definitely be much better and more precise when we will have more next generation polar orbiters in the orbit. Of course, there will be many new in-house products that will include cloud microphysics and water vapor content, which are not currently available with AVHRR. These will be very important for forecasting and nowcasting applications, but more about these level 2 products you will hear in the presentations tomorrow, so I will not go into that now. And just to sum up, while preserving the legacy of the AVHRR, METimage will bring many innovations and improvements. It will offer much better spectral and spatial resolution. It will enable production of many new RGB combinations and even better precision of measurement, especially over high latitude areas. By this, it will offer a breakthrough in many application areas, as we could see, by providing new advanced products such as cloud products, including microphysical analysis, sea surface temperature, vegetation products, or other land products, snow cover, fire monitoring, and also aerosol products, and of course, polar motion vectors, but certainly many more. So for me, and I hope also for you, it looks like a very exciting future in the applications to look forward to. And with this, and with this nice VIIRS daily composite image that mimics view that will be soon available with METimage, I thank you for joining this webinar.
Thanks, Natasha. It's again interesting, Natasha, to look at I mean, how exciting it will be to look at METimage like this. I
Yes.
think you also try to put in a nice complementarity between the geostationary and low Earth orbit satellite. And I think there are a lot of studies needed on where to use them and, where exactly we, for example, the nowcasting application where we do.
Yeah, sure.
I think more studies are needed there to establish this, but it's clear from the presentation that there are opportunities. Okay, I think I will have a look at the questions that you have. I think there's one question: which channels enable the distinction of snow and thin clouds in the snow RGB? I think it's this nice picture that you had, right?
Yeah, I had this nice picture of.
Do you want to show it? Maybe.
Yeah, I'm trying to. Yeah. Okay. Let me try to share it again. I don't know whether you see it.
Yes.
The daytime snow RGB.
Mm-hmm.
So the channels that are here available are 0.6, 1.2, and 2.25 micron channels. So microphysics is given by 2.2 micron channel. 0.6 shows the clouds clearly. So I guess the difference between so if you look at the colors, I would say that the 2.2 micron channel is actually the most important one, but I would have to check exactly the colors to be able to answer this question. So, but the channels that I used in the RGB are 0.6, 1.2, and 2.25.
Yep. Maybe we can explain.
Yeah, maybe I will. Yeah, I will check and write the answer in the Slido.
Yeah, no problem. Thanks, Natasha. So now I have to bring back my screen. Okay, let me have a look. I think that was the only question. Oh, no,
Okay,
there's
yeah.
more. RBS and AVHR imagery used in northern latitude, now casting today.
Well, I guess this should be answered more by the forecasters in the northern latitude, but I know that there are applications also in nowcasting using AVHR imagery and VRC imagery. So definitely yes, because in very high latitudes, geostationary imagery have a rather poor quality and a large parallax shift, especially with high convective clouds.
AVHR imagery is one of the large used products from EUMETSAT, actually. So
yeah, so I'm sure yes, they are used. Yeah.
Okay, if so,
okay.
I think we had a nice day today. I thank all the presenters, Pepe Phillips, Andrea Miraner, and Natasha Strelek-Mahowicz for your presentations. And thanks everyone for attending this. And we look for tomorrow where we have the next generation, we have the FCI METimage level 2, geophysical level 2 products and application perspectives. I hope you all join back tomorrow. And until then, I say goodbye to everyone. We will make also all the, like Stefan says in the chat box, we will make all the presentations and the recordings and the Q&A available to everyone. Thank you. Have a nice evening. Bye.
Thanks, bye.
Bye, everyone.
Bye-bye.
Bye, thank you. Bye-bye.